Welcome to Talk Universe. This is our show for Wednesday, October 5th, 2016, and a wonderful show it is going to be. It is all about computing and mathematics, and in fact, it's entitled Mathematics and Modeling. Now, modeling isn't what you think, women going down the runway or guys showing off their new jeans. Modeling in this case is constructing a logical and mathematical model of something so that you can play with a model and interrogate it and learn from it, instead of having to deal with the real thing. I think that if you're dealing with, let's say, a hurricane and its effects, you'd be far more inclined to do the research if you could do it in the safety of your office. And a model of a hurricane can perform very much like the real thing, but in the space of a computer, and we use it to make weather predictions about what will happen. So the models have gotten very good lately. And behind it is a series of equations and algorithms, methods of getting things done, and the mathematics behind it. So tonight we have an interview with a fellow who works with, I would say, the world's foremost company in mathematical modeling and computing. And so we're going to get into that very briefly here and talk about his take on what it's all about. And you'll really be fascinated to hear what he has to say. So what is modeling? It's creating an image of something that is functional. It's not just like a picture of it or a plastic knockoff of it, like a plastic car. What we're talking about is a dynamic mathematical structure and logical structure, like a computer program, but it acts like a real thing in the real world. And we can use that model and we can test it. We can push it to its breaking point. We can find out exactly what will happen. Now, what's the advantage of this? Well, let's say I wanted to find out how a Rolls-Royce would act if I ran it over a cliff. Obviously, it's going to cost a lot of money to take a real Rolls-Royce or 3 or 4 of them and run them off a cliff and see what happens. But if I had a computer model, I could do whatever I wished, and I wouldn't have lost the investment on that car. The car wouldn't be destroyed. And yet, if the model is good, I can learn an awful lot about how it will break or fail and what forces it'll take to make it act a certain way. And, as stated previously, you're not going to destroy a real car. Dynamic models of things such as hurricanes or weather systems are used all the time to predict how it's going to work or what's going to happen, and they have pretty good accuracy. More accurate would be models of aircraft that they're building or models of computer control systems. So we can create a model of a thing, and we can use the model and learn a lot about the system, even to the point where we can end up designing the system using our model as a guide. So think of it as the spirit of the thing brought to life in the computer. And this is what we're going to be talking about. And mathematics and programming are tied together. They're at the heart of creating these models. Now, models aren't just limited to things like the weather. We obviously can make models of aircraft, and they do it all the time before the first rivet is put in place. And we also can make models of hurricanes and weather systems, and they work pretty well. Recent advances have shown that we can model what's happening in an earthquake to a high degree of accuracy. We already model, nuclear weaponry to expand our knowledge of how they operate without actually detonating a nuclear weapon. And the simulations have gotten extremely, extremely good. Now we have simulations that can take, for instance, your genetics and figure out a lot of your characteristics without actually ever seeing you. We can take a tiny sample of your tissue, we can analyze the genetics, and create a model that would look a lot like you. It would give you basic characteristics, your height, your build, your hair color, that sort of thing. So models have a lot of usage, and we've reached a point in our world where we depend on them. And they're basically mathematics brought to life. A model is the spirit of the thing brought to life in the computer. And we're going to be looking at the mathematics behind those models and how they are brought together, how it works. We'll get into a few interesting things like algorithms, methods of doing something by rote, by the book. An algorithm is simply a series of predictable steps for doing something. And that's the rule of the day in a computer. So this is really a fascinating subject because everything in the universe is made of mathematics in one sense or another. What's interesting about that is no matter who you are, no matter where you are in the entire universe, your math and your chemistry and your physics will be the same. And so mathematics can actually serve, in a sense, as a universal language. So there's so much to learn about mathematics, and people, tend far and wide to avoid mathematics like the plague. And that's really unfortunate because it's a fascinating thing. And when you understand a little about math, It gives you a handle on things, a means of controlling and understanding things that you couldn't have any other way. Now, sometimes a computer model has nothing to do with physical objects or things that you can wrap your hands around. Many times a model will be an abstract concept, a mathematical concept, and it might be how a population has grown or how its members might have moved over time, or, by analyzing that, we might determine that the climate had been changing in their area or something along those lines. So many times a model is something that is more fundamental than what we see. It's the underlying principle behind how it works. And we look at things like consumption of rare materials like cobalt or samarium, and we can determine what sort of industry is going on in an area. And we can look at the heat being exhausted somewhere, and we can determine how much energy is being consumed. So we create models that tell us things, and then we can look at those things and use them as indicators for a process. The model can be abstract, or it can be very close to something in the real world that has a more physical form. Now, I mentioned models and water usage, and there's a very good reason for that. Many people are familiar with the Anasazi Indians that vanished about 700 years ago, and nobody knew exactly where they went. And they couldn't figure out why these people made these amazing cliff dwellings, these villages, unlike anything they'd ever seen before, and simply packed up and walked away from them. And so it fell to a few researchers to analyze things that they found, signs and bits of information, and to create a computer model and to try and figure out where the people went and why. And what they found was that the water in the area was drying up, the local climate was changing, and it was making it extremely difficult to grow their crops. And over a period of time, a few generations, 3 or 4 generations, they had effectively moved out little by little looking for literally greener pastures. And what was most interesting about this process is when they constructed the model predicted that they should find settlements in certain areas around a valley. And when they actually went to those places and did the archaeological work, they found that indeed the proper number of home sites was discovered. So the model was actually very accurate and helped them come up with a very credible answer to the question, where the heck did these people go? Why did they simply vanish? So it solved the mystery. Building this model and putting their information in from the real world solved the mystery. So we can see that there's a lot we can do with a model, and we've actually gotten some real-world results out of some of the things that were done recently. Wolfram Mathematica is a symbolic mathematical computation program, which is basically a mathematics programming language, the Wolfram language. And it includes a huge number of databases of information on dozens of different topics, including people and history and chemistry and physics and populations and art and language. So just about any subject you can imagine, there is a database for that's included with this program. And it, in my estimation, is an incredible body of work. And it was conceived by Stephen Wolfram and developed by Wolfram Research. I might have mentioned that I read the book, A New Kind of Science, a while back, and I was quite impressed with it. So the opportunity to get somebody from the program and from the company that did this development was something I couldn't possibly pass up. So we're going to have a guest, Jon McLoone. He's the guest on the show tonight. And he does international business and strategic development for Wolfram Research, and he's worked with them since 1992. So we're going to have an opportunity to consult with him and find some of his views and learn a lot of things about mathematical modeling. I have to admit, mathematics is one of my favorite subjects, and so many of the things that I do in my work end up taking me deeply into mathematics. Just recently, I was designing a circuit where I had some electronic noise that I needed to filter out, and the only way to know what sort of filter to build without just randomly putting parts together is to literally calculate time constants and values and arrive at a mathematical solution. Today on Talk Universe, our guest is Jon McLoone, who has worked with Wolfram Research, the makers of Mathematica, since 1992, working on software development, system designs, technical writing, and strategy. He supports educational projects in cooperation with universities and government research and has lectured on Mathematica around the world. McLoone has a degree in mathematics from Durham University He currently has two major roles at Wolfram Research in Europe, Director of Technical Services, leading the consulting team, and Director of Technical Communication and Strategy at Wolfram Research Europe, principally responsible for the directions that the company takes on technical strategy, business policy, and projects with external organizations. He also acts as a spokesman and evangelist for the company. He also is co-founder of ComputerBasedMath.org, a project to redefine school math education, assuming the use of computers. And Jon, welcome to the show.
Thank you very much.
What brought you to mathematics, really?
Well, I guess the way a lot of people are, it was easy. When I was at school, it just came easily to me that I didn't ask too many questions and took on rules easily and could live in my head quite well. And so naturally one ends up doing more of what one's good at and less of the things like sports that I wasn't good at. And that sort of followed straight through into the natural treadmill of education that took me to university, and I studied maths at Durham and did a degree. And at that point, probably I would have gone off in some other random direction, but it was sort of luck that stepped in at that point and found me a job at Wolfram, where I really discovered more breadth of maths, its applicability, and the fun of it that had a little bit been lost at university.
Absolutely. There's a term, illiteracy, for people that can't read or write, and we know that's a tragedy, but innumeracy is a term that a lot of people aren't familiar with, and it's really the inability or not desire to work with numbers in any capacity. Is innumeracy, in your opinion, a great tragedy for society?
Well, yes, although actually I have some trouble with the term numeracy anyway, because it focuses very much on the numbers side of mathematics. And it sort of obscures a little bit some of the wider benefits of mathematical thinking. So you can contrast sort of numeracy being typically, when you look at the governments in places like the UK where I am, or in the US, there's a big sort of focus on can you do mental arithmetic, can you calculate interest on something, these sort of very numerical calculations. And it really takes some of the emphasis off the computational thinking and sort of logic of mathematics as well. So yes, it is a problem, but I think you can break it into several different problems. There's pure innumeracy. There are people who can't count, but really in developed nations, that's not a major issue. There's a lot of people who don't think with any quantitative intuition, which I think is actually a much bigger deal, that they could sit down and do long division on their credit card, but they just don't think about the fact that 20% interest is really high when it compounds over several years, and there's sort of a lack of intuition because they've spent all of their time being put off the maths by this sort of endless treadmill of doing computation, and have decided that they're not mathematical people. And that's a particular problem here in the UK, where you get perfectly intelligent, respectable people on the radio who will laugh and say, oh, yes, I was no good at maths. And I think the US has a little bit of that problem as well, that it's become acceptable to not be good at maths, when really most people who are saying that don't really know what maths is. What they mean is they were no good at learning their times tables or doing long division. And it stopped them seeing the kind of breadth of what it really could do for improving their lives. And I think that kind of ability to think in a logical and mathematical way really is the thing that would improve a lot of our lives, plus the ability to estimate, which there's too little emphasis on. Whether or not somebody knows their times tables very well, actually, I don't think is a great tragedy as we get to the point where it's so easy just to find those trivial computations.
Well, I think you're absolutely right. Most people can't even estimate well. They don't even know if they're in the ballpark, and it's because they don't get, I suppose, a mental or visual image of the process and the relationship. And they miss getting a whole handful of tools they could use to give them a little more control over the world around them. So how do you enable people? I'm sorry, go ahead.
Well, so I think one of the key things in that of being able to do things like estimate well is experience. And I think that gets mixed up in education a little bit with practice. And so there's a lot of practice done on how to do computations, but actually in terms of experience of the answers, most of the time spent in the computation, and you're so relieved to finally get to the end, you don't think about the answer very much. And so what we really need is more experience of the situations and the context. So you start getting a sense of, is that a big number? Does that sound plausible? When we're working on problems, quite often we have a sort of game of intuition at the beginning. And it's surprising how even as professional mathematicians that sometimes you have very little intuition for a problem because you're so reliant on, well, I'll do the calculation and find out.
Sure.
Typical thing. You can ask somebody, is it likely you'll get 7 heads out of 10 coin tosses? And I think most people have a good intuition that that's kind of slightly less than the half, but perfectly likely. But a lot of people then, if you ask them, well, what about 70 out of 100 or 700 out of 1,000, they completely lose any sense of intuition. But a lot of people then, if you ask them, well, what about 70 out of 100 or 700 out of 1,000, they completely lose any sense of intuition, and it comes as a surprise to them that it's an extremely rare event to get 70 out of 100, and it's a kind of never in the life of the universe to get 700 out of 1,000.
Yes.
And, unless you start seeing with these things and playing with more mathematics, especially in context, and asking yourself, do I believe that answer? Then you don't ever build up that experience.
It's sort of recognizing the graininess of the numbers in a sense. There's often a statement among mathematicians that there's a shortage of small numbers. So how do you... Oh, I'm sorry, go ahead.
So I was going to say there's a nice book on stats that says that all you need to know about stats is to ask yourself the question, is that a big number? Especially when you're listening to things like government statistics and they say we put 10 million into this project. And well, if you divide that by 260 million people, that's no money at all. Right. Whereas something that's going to cost each person £1, well, that's quite a lot over all the people.
So how do you enable people to become familiar with and do mathematics successfully?
Well, that sort of leads to my major project, which is the computer-based math project, where we're trying to start again with what a maths education should look like. And we've asked ourselves this, you mentioned it in the intro, this sort of basic question of if we assume that you've got a computer, then what do you need to know to be a good mathematician? And a lot of it comes down to trying to teach a kind of problem-solving process rather than letting that happen by some kind of magic that happens by doing mathematics. And so we talk about there being sort of 4 steps to it's slightly arbitrary slice, but it's good to have a sort of meta process. And our 4 steps are kind of asking the right question. What do I know? What don't I know? What am I trying to figure out? What maths do I know that might help? And then there's a translation step, which is, the abstraction, turn it into an equation or a graph or whatever your representation is. And then there's a computational step, which is take those equations and solve them or find the roots or whatever the operation is that you might do. And then there's a kind of reverse translation step, coming back to what does that mean in the context of the problem with which I asked the question? And do I believe it? And how do I validate whether that's correct or not? And the thing that we've come to realize as we work through this over and over again is that current sort of traditional education is consumed by the step 3, the computation, that we spend hours of our lives learning how to do integrals by hand or how to solve equations and how to move the variable from this side of the equal sign to the other and swap its sign and all of these rules you learn. And it squashes out the how do I turn this real world problem into some kind of mathematical representation? What are the concepts and what goes wrong with this concept? And so what we're trying to do is to reframe everything in the context of you have a problem, here's a meta process, let's walk through that process, initially scaffolded where you're shown how to ask the right question, how to translate. Maths gets introduced in consequence. And so all of our problems, we start with a question like, how tall is the tallest woman in Estonia? If we don't know the answer, can we make an estimate? And
sure.
The mathematics you need then emerges from the problem. And it's so opposite to the way most of the time it's taught, where you sit down and say, right, today, class, we're going to learn about limits. And it's so abstracted away from its usefulness. That's what turns a lot of people off, I think, who rightly say, when will I ever use this? But it also, I think, obscures the concept very often, which is driven by a need and driven by something that in a context makes a very concrete sense. And then when you see it in a new context and then in the third context, you start seeing the commonality of the abstraction. But when you leap straight into the abstraction, you're kind of cut off from this usefulness that is in the end why maths is this sort of, along with one's native language, the 2 compulsory subjects pretty much in education, because they're so useful. And we hide the usefulness, which is a big tragedy in the education.
Well, I've often felt that we fell so far behind on the space program because of the fact that in the beginning, engineers used a slide rule. They had a really visceral feel for what the problem space looked like, what the problem felt like. And now we have a bunch of people who think they can put some numbers in a computer and that's the answer. And they haven't even a clue whether it's within an order of magnitude of reality. So I think that the model of using a slide rule actually was very helpful for helping people understand the relations of numbers and how they really apply to the problem.
Yes, there is within a certain limited space that we're able to deal with, then having actual hands-on, treating it like a physical thing, like a slide rule. And we make these interactive things on the computer that you can slide sliders and press buttons, and you actually got your hands on the problem and you see the graphs update in real time, that kind of thing. That's great up to about 3 or 4 dimensions that the human mind is capable of mapping to something that we can relate to in the real world. It sort of breaks down when you're talking about a 10-dimensional problem, or when you're in a context where there isn't an intuition. If you're building a bridge and you want to work out the thickness of a cable and you get a 1 kilometer thick cable, you've got a real intuition. You've never seen a bridge like that. It's probably wrong. In electronics, if you get something that says it's you need a capacitor that's in millifarads or microfarads, you don't have that intuition to know that seems like an odd component to put there. So this is why in our sort of step 4, I mentioned the idea of asking yourself, do I believe the answer? Is it right? Which, when you're in a computer-based world, you have to assume that there are potentially bugs in the software anyway. But really, as problems get more complex, you can't know that you've even asked the right question, or that you haven't mistyped something, or that you just got something conceptually wrong. And you don't have the intuition because the answer comes back out. It might be very distant from the reality. And so what we want to do is to help to build meta processes again for how do I test that? Can I do the calculation using a different concept and corroborate it? Can I reverse the process? If I'm doing an integral, can I take the derivative and get back to where I started? These kinds of things that you can do to try and check what you've done. If I look back at my classic education, I guess most of us went through, and I thought about how did I know I had the right answer in those days? And I figured it broke down to about 3 things. There was check you're working. That was always lesson number 1. Go through it again and check it. Well, you're building a bridge with 10,000 components. How can you check your work? That's not a feasible approach. There were a lot of problems that said show that A equals B. And when you got to B, you knew you had the right answer. And if you didn't get to B, you knew you hadn't. And then the other problem way that you had was if it came out as a nice, neat little thing like a half or a quarter or square root of 2 or something, you were probably right. And if you ended up with an algebraic expression that started not being able to fit on one line of your A4 paper, then you were probably wrong. But of course, in the real world, you do have problems where you get a mathematical expression that can be many pages of expression, and it's perfectly correct and perfectly useful.
String theory, perhaps.
Sorry?
String theory, perhaps.
Yes, and there was a proof that made the news recently, wasn't there? It was 4 gigabytes or something of data that was the solution. And so these sort of pencil and paper type checks don't apply when you start getting into this more modern world where maths is so much more scalable and applicable. You have to have new methods of validation. And intuition is a part of that. Can you make an estimate before you start? But it's only one out of a whole bag of tricks that we ought to be teaching, again, as part of teaching explicitly the process of how do I solve problems, rather than, solve some equations and integrals for a few days and eventually you'll figure out problem solving by chance.
Sure. And I often think of it as a microscope. When we talk about microbiologists, we see that their tool primarily is a microscope because that's the only way they can see what they're working on. And when we get to mathematics, it is of such complexity and depth that many times we need a microscope of sorts, and the computer serves as that window or microscope. Yeah,
absolutely. It serves as a second purpose as well, which it brings that is new, which is it's a laboratory. That you can do mathematics by experimentation in a way that you couldn't before. The cost of doing some calculation was so huge. You only set out on the one you knew you wanted. And now you can just say, well, let's just work out what this thing would be for all of these different values and see if any of them look interesting. And the cost is so low that you can just try things in a way that, I'm sure some people would think that sounds terrible, that you just fumble around and sometimes discover interesting things. But it's worked for science for centuries that, sometimes you just mix some chemicals and see what happens.
Well, it worked for natural selection too. So there's a lot to be said for it. I think that a lot of people see numbers as things to count with rather than being descriptive or transformative. And how do we get to the point where we can explain the difference to them?
That's a fairly tricky one. But my feeling, which we haven't really explored yet in the materials we're building, is that again, if we, just from an efficiency point of view, if we save the time that's spent doing hand calculations, or at least where they're not conceptually enlightening in their own right, then we have room to do more mathematics. And so we can introduce concepts that are further removed from pure numbers. Up to the age of 18, I had never learned anything that involved, things like, I'd done no graph theory. I knew nothing about Fourier transforms. There's all these kinds of bits of mathematics that are considered, A, there's no time for in a curriculum, and B, that are considered too difficult because proving how the formula for Fourier transforms works or knowing the algorithm behind an FFT numerical computation is very complicated. But if you just accept that this is a tool you can use, then actually it's quite accessible. You can take a sound and you can plot its frequencies. You can talk about what the spikes mean and what the troughs mean. And that's actually very accessible. So I think if we could introduce more mathematics into mathematics education, then you would get more exposure to things that are not just counting, that you would start understanding there are different ways of structuring knowledge and representing ideas, and that there are different tool sets that allow you to transform these slightly more abstract structures like a graph into something else that is useful. And you can start thinking in different ways, which in the end is surely the real value of mathematics, is teaching us to think in a different way about the world.
Absolutely right. Yeah, I have to agree with you there. It's been suggested, and this might be a little off the wall, that reality might actually be a simulation, or that the universe acts as a computer. And there's some evidence to support that to some degree, but not enough to make a decision about it. What do you think would be the implications if we found that the universe really was like a massive computer or a simulation?
Well, yeah, I'm quite happy to believe the idea that the universe itself might be simply running a computation, that subatomic particles are just the gates flipping open and closed, and it's calculating the consequences of its initial conditions. I'm not sure I subscribe to the idea that it's kind of an engineered thing that some higher force might have created as with a plan or intent. But I think we're heading away from maths into religion now. But in the end, it's a question of if you believe in fate, it's the same question. If you put in a kind of more philosophical context, that if our actions are all predetermined, does that change our ability to make decisions? Should we just give up trying to think about things because what we're going to do? And in the end, if you can't calculate it faster than it's going to happen, then it's still effectively like magic or like a mystery to you. So you might as well continue to believe that you have free will, even if you might actually just be acting out the consequence of the current neuron states of your brain. So I think there's a danger if you start thinking about it too deeply, you just give up on everything seems pointless.
Right. You just accept it as, that's what it is.
It's probably true, but who cares, I think is my philosophy on it.
Do you see it? I'm sorry, go ahead.
There, and unless you can use that knowledge to do something different, to affect it, then it makes no difference to you.
Right. Yeah, from the practical standpoint, you're absolutely right. Do you see a time that math will emerge from something that's under the hood of applications and become something that more people can appreciate?
Well, I think I kind of actually believe it should go in the opposite direction. That human progress from the beginning of history has always been about raising our activities to a higher and higher level. We build tools to allow us to not have to do that stuff anymore. We build cars so we don't have to walk. We build combine harvesters so we don't have to stick seeds in the ground one at a time. And it frees more time to do things at a higher level. And mathematics is exactly like that. We prove things so that we can then say, right, that's known. Now I can cite that result and not have to think about it again. So What I want to see is more mathematics becoming available as a given that we can just trust because it's been built or it's been proved or whatever, and we just take it for granted and hide from it. And your analogy about under the hood's a good one, actually, because when I was young and poor, I had a car that in order to use it, I had to periodically go under the hood. I had to, for some reason, the fuel mix would get askew, and I'd have to get out and get a screwdriver and fiddle with it. And I'd have to know these intimate details of the engine of my car in order to be able to drive. And, I consider my life much enriched by having a newer car now that I don't care how it works. Somebody has to. We need automotive engineers to build cars, but we need lots more people who can drive places and do things with cars than we need to build them. And the same is, I think, true of pure mathematics. They're really important. There's people making new abstract discoveries that may loop back and turn into something practical and useful later. But it's not the mainstream thing. The mainstream thing that the whole of civilization should be aware of is using these tools to be able to say, okay, I can calculate the following because somebody's proved it, come up with an algorithm, somebody's coded it into the computer. Now I can wield this tool and do things that my predecessors couldn't. And I think our attitude in traditional maths education is kind of unique amongst subjects in that there seems to be a belief that you're not allowed to use a tool until you can fashion it for yourself.
Right.
And you can't imagine woodwork being like that. I want to make a beautiful carving, so I'm going to have to fashion a chisel and learn how to sharpen it really well before I'm allowed to use it, or I have to be able to make a rotary saw before I can saw things with it. If we get the concept of what the tool's doing, we can just use it. And then we're straight to, let's make something nice out of a piece of wood. And I think maths should take more of that attitude that unless there's something enlightening about knowing how it works, or it's still a practically useful thing in doing the computation, because some things, the algorithms have points they break down. It's useful to know where their failures might be. But unless there's one of those two motivating reasons, let's just take the tool and use it and then think about higher maths problems rather than kind of constantly reinventing 19th century mathematics.
Sure. Okay, we're going to take a break right there, okay? Stand by. We're back with our guest, Jon McLoone, and we're going to pick up where we were. Jon, tell us a little bit about your work and the products that you develop.
So my day job, as I said, is at Wolfram Research, and Wolfram's mission is to try and automate all of computation. So that sort of explains where some of my views come from, because we've been trying to build sort of a single integrated software platform that does all of the automated mathematics that has been invented so far, that in a way that's kind of algorithmic. So you know, on the one hand, you can think of it like a supercalculator where you can type in, you know, any symbolic integral and get an answer out, or take some image and say detect the edges on this image, or some machine learning, all of these different kinds of computation, but a lot of the work's to try and make it all fit together, so it's not a random collection of tools, but one coherent whole. So that's been my sort of day job for getting on for 30 years now, and seeing that develop and trying to influence the design and directions of that to include what people actually need to get work done. And so part of that, I travel around a lot talking to people and being constantly surprised by things you think were solved problems, and discovering that in every field of engineering and science, there's always new work going on in things that seem like, you know, I visited some people who make electric motors, and you're thinking, electric motors, they've been around for 150 years or something now. Surely we kind of know how to make those. No, there was new problems in energy recovery and efficiency which required complex modeling and optimization. And this is going on all over the place. So that's what I spend most of my time doing. And at the moment, I lead a team on top of that takes the technology that we've been building up for the last 30 years and tailors it to particular problems. So I have a little collection of programmers and scientists who take a diverse collection of random customer problems and try and solve those. And so we sort of come in with a fairly detached point of view, because we know computation really well as a team, but we don't tend to know any of these vertical disciplines. So sometimes that's problematic. So you have to work with them to get the domain knowledge to be able to figure out how to solve their problem. And sometimes it's a real benefit that you can not be distracted by assumptions. You can just treat it purely, particularly in data science, that we did some work for the National Health Service here in the UK. And it was quite beneficial to not know what a lot of the column headings meant in this huge data set we were given about customer safety, because we weren't swayed by thinking that certain thing must be true. And we just plowed through the data and looked for interesting correlations and sort of significant time series within the data, and came up with some interesting conclusions about whether you're more likely to fall and what triggers that just comes naturally out of the data.
Right.
So I have spent my time on three things of doing very practical technical work, solving people's problems, doing more imaginary, visionary technical work in trying to guide the development of Mathematica to being the kind of most universally useful thing that it can be, and this very philosophical work of trying to rethink maths education through my work in computer-based math. And between those three things, they pretty much fill the day.
I see. In the past, people would often make an analog model of things, like 3 weights on a piece of string, and one weight would represent the cost of transport of fuel, like coal, and another one would represent the location of an ore source, and then another would be your water transport system. And they'd take a map and they'd drill a hole where these 3 things were, and they'd drop the weights through. And wherever the knot on the string ended up, they'd say, that's where we're going to build our steel mill, because that minimizes our costs. So they'd make these analog gadgets, which acted as a model of the problem space. And that gave us some capabilities we didn't have before. So how do you think this sort of modeling changes business?
There's a very similar one as well, which I've seen, which was doing structural calculations for cathedrals, whereas you hung weights on strings, but you modeled the cathedral upside down, and the shapes that the strings formed were the arches that you needed to build in order to distribute the load.
Right.
But in the end, these are tools of the moment. Just as Mathematica is the tool of the moment for a lot of calculations, and now instead of hanging weights, I would type in, find a minimum of some set of constraints and equations and get an answer. And maybe one day that will go away, and Siri will just become so fabulous I'll be able to describe the situation in verbal terms and get an answer. But the tool is a means to the same end for all of these things. It's, can we make better decisions with the knowledge that we have?
Yes.
And mathematics is at its heart is a process, and one of the most successful processes for getting answers given knowledge. There are others that can approach these things entirely emotionally. That's one solution, and I suppose one in some fields you can approach it theologically. But there have been other things that have come and gone. But the reason why mathematics is so important is because it's just a fabulously successful way of getting answers. And so the thing one has to turn around to then is say, well, what are the answers that we need? What would make the world better? And a lot of these things are just, in the end, they're optimizations. The example you're giving, you're finding a kind of an optimal value. And our world is full of things that we think if we could just be a bit more efficient or a bit more optimal, or know how to choose between choice A and B and which is better. I think optimization and best comes down to the final answer on a lot of things.
Well, yeah, but what you mentioned earlier about free will and possibly the universe being, on a track. If we have perfect algorithms for everything and we always know the proper answer, doesn't that in a sense eliminate a portion of our free will? We have to make the right decision.
Well, that's a good thought. That maybe another 1,000 years in the future we'll reach that point where everything is just so well engineered that we have solved life, and we will know that given that my aim, maybe this is an axiomatic choice to say I want to be happy, I would know what all the choices are in my life that will maximize my happiness for my lifetime. But we're so far off that at the moment that for a start there's a whole bunch of questions about what do you actually want to optimize, which is a lot of that itself is a question that lacks any machinery to choose. Is happiness what I want to optimize? Or do I want to optimize longevity? Or do I want to optimize my impact on other people and their happiness? There's a lot of choices before you even get to trying to then figure out, can I even answer that question? So, yeah, maybe we're heading like lemmings to a cliff towards some horrible future that actually won't be great. But if we get really good at it, then presumably the choices will tell us to stop studying at some point.
It'll be terribly optimum.
Yes.
Well, let me ask you something.
But today there are just so many opportunities just to do things better, and that I think we're a long way off that. And this, in the end, is a lot of what I get with these industrial problems that come in for my consulting team is, things like we looked at a problem for getting salesmen and engineers for a company doing Windows to be able to be sent around different appointments better, and when do they offer the appointment to the customer, and it's it's a traveling salesman type problem, which is well solved in the ideal case, but once you start throwing in the constraints they had, it becomes an interesting new problem that they got contracts with the engineers that mean they can only work certain hours, and some of them are on different contracts, and how do you figure all that out so that it's optimal for the engineers as well as for the company? And there's a lot of unanswered questions in the world.
Sure. So what would you say is your definition of a mathematical model?
It's, in a very general sense, it's a structure of information which you can process in a predictable way.
Yes.
Which sounds really vague and unuseful in its own right. So it depends on the kind of model. But in the end, you're trying to abstract something you care about to a representation that you can run reproducible behaviors on. So in that sense, I don't see any difference between mathematics and, say, a computer program,
right,
because they're both ways to represent something where operations can be performed on it. And, in my mind, I think of mathematics really as being the first programming language. It was a programming language that was optimized to be run on a human brain rather than on a, electronic machine. But when you write down an equation and say, solve this equation, that's a program. It's an abstract specification of the real world, in this case represented as an equation. And then you've got an operation that you're performing that will run that program and produce a number which is useful to you. And that's no different from saying, here's 5,000 lines of code and I want to operate on that on the computer and something will happen that I hope will be useful to me. So a model is just anything where you can just put it into something where you can operate on it.
It's a representation of some real world system that we're interested in, basically, right?
Yes. We spent, actually, as a team, we were working on how do we describe, trying to find a word for model that was more general. And I'd love to hear if anyone has a good idea. We were talking about, well, is it an abstraction? Is it a representation? Because a model is too narrow in most people's minds because it represents things that are like a system of differential equations or equations but there are things that, if you draw a diagram, it's a model of a kind. It's a representation. When I turn some surveying thing into a map, that's the model. It's not, sure. The map isn't the world. The map is something that represents the world.
Well,
and
so modeling,
do,
modeling has given us a lot of ability to describe everything in numbers and equations. And I think that's one of the most powerful things there. So we can model the spin of a quark or the growth of a flower or the action of a typhoon, and we can do it in the computer, and it takes on some of the aspects of reality. So what do you feel is our most powerful modeling tool or technology in this sense?
Well, it has to be the computer, because it allows all this machinery of modeling that we've been building up to be scaled both in size and in performance to be suddenly massively more useful. And where models break down, they are typically breaking down, well, they may break down because your fundamental theory is just flawed, of course, but often they break down because in order to compute them, we have to simplify them. We don't build that full simulation of the universe yet because we can't compute with it. So we start assuming things and say, well, let's ignore air resistance and let's ignore this and that, and let's assume that this thing is a perfect circle and these kinds of things. And we make it simple enough to compute with in the hope that the things we've thrown out aren't important. And sometimes they are. They are what makes your model useless, because the errors that you've introduced with these approximations accumulate. And the computer lets us go a lot further before making those kind of assumptions, because we can code up a lot more, because we can do things like scan objects and actually get their shape rather than assume it's a circle. And they allow us to not hit the bottleneck of computation for nearly so far. So we can leave in all those details, because before we had to throw them out, because otherwise you'd be computing for the rest of your life.
Right. Yes.
And so the computer's the tool for driving the usefulness of modeling. And if you look at the world, you can see that the growth of computers and automated mathematics, with things like Mathematica, following this history from we launched the first version of Mathematica pretty much as the personal computer started to take off back in 1988 was when the first version of Mathematica. So we've ridden this wave all the way through. And what we've seen through that time is that fields that were never mathematical before have become mathematical. So things in biology, you didn't really try and model back in the 1980s because maths didn't seem very useful there. Maths was useful in certain parts of engineering and physics where the models were quite simple relatively, and so it had been tremendously useful in those fields, but it hadn't found much use in a lot of these other fields because the models were all kind of messy. They're dealing with the real world, with when you're doing political geography, dealing with all that sort of mess of, well, you've got roads and railways and rivers and things that affect the flow of people and goods. It's just too hard. And now computers have made it not hard. Maths is creeping into all of these subjects. I've dealt with people doing computational archaeology, using satellite photography to try and automatically detect burial sites. That before, when I was going through university, archaeology was strictly a shuffling around in the dirt, scraping things with a trowel kind of science.
Right.
And now it's mathematical. I once embarrassed myself in the early days when I met somebody from a zoology department who was interested in Mathematica, and I said, "Oh, zoology," and I revealed my surprise, and he looked down at me and he said, "Yes, well, Monday through to Thursday is stroking fluffy animals days, and Friday is hard maths day." And so, okay, I put in my place. I will never assume that a subject is not mathematical ever again.
That's a great point. What would be, in your mind, the most exciting contribution that math has made to our lives?
Most exciting. Well, you can look at this so many different ways. Obviously the exciting thing of the moment is computer computation, and I think machine learning is a very exciting area right now of for the first time being able to solve problems like what is in this photograph in a very kind of relatively easy way. But if you look for more profound, then I think things like navigation probably account for a lot more, and astronomy, being able to do calculations on where you are in a year by looking at stars. And being able to navigate by the stars, the kind of geometry needed to make that stuff work probably had more to do with getting us where we are today than this relatively recent thing.
Sure.
But I'm going to hang my coat on something much vaguer, which is that I think it's logical thinking. That is through maths.
You know what? I like that.
It's rationality. It's the thing that really separates us from the animals. Yeah.
Well,
animals higher animals have emotions and they can think emotionally just like we can. They aren't as sophisticated at storytelling and artistic endeavor as we are. But I think the profound difference, which we have developed through this machinery of mathematics, is rationality and saying, can I come up with a rule that will guide my behavior or help me to make a decision? And understanding cause and effect and consequences, these all kind of pure logic kind of ideas all come out of thinking in a mathematical way.
Well,
and we'd be a very different civilization, fighting all the time and scrabbling in the dirt if we didn't have that.
Absolutely. Well, Jon, I'm out of time, but thank you so much for coming on the show. It's been an interesting interview.
Well, great fun.
And I hope that we can do another one soon.
That would be fun, yes.
Okay, well, thank you very much. I really found some interesting comments from Jon McLoone in our interview. And the thought that mathematics is a language, like a programming language, that's a very salient thought. It makes a lot of sense. I know that many of the things that I do, I see in terms of language. And when you build a thing, for instance, if you build a vehicle, you lay out all the designs, the parameters, you know what metals you're using. You have an idea what it's going to weigh, how much force it takes to bend the parts. If you've done any mechanical work at all, even welding or drilling, or just assembling things, you have an understanding of it, and it's an innate understanding. But when you begin to measure things, and you weigh them, and you see how big they are and how dense they are, and you add that understanding to your physical understanding of it, how it feels kinetically to pick up a certain piece of metal, when you put the numbers on it, it expands your ability to think of exactly what it implies. I know that if I pick up a bag of something that's heavy, I could pick up maybe 2 or maybe 3, and I might not know how much it weighs, but if I know exactly what the weight of that bag is, and I know what my limits are, what I can pick up by measuring in the past how much I've been able to carry, I can tell you I can pick up 3 or 5 of those, or I can't. The numbers will tell you without actually having to do the experiment of trying to lift them all. When we begin to assign numbers, quantities to the things around us, we begin to get a broader understanding of it. One of my favorite sayings was, and this is a little bit of a misquote from Lord Kelvin, was, when you can measure what you're speaking about and express it in numbers, you know something about it. I think that's a very good way of putting it, because most people speak right off the top of their heads without really having any sort of solid knowledge about a thing. You can't argue with a number. You can take a measurement and it's right or it's wrong. We've all run into people who are New Age or mystical or have a bent to saying things that make you wonder. And one of the easiest ways to make them angry is to ask them to give it to you in numbers, exactly what it is they're talking about, how much, where, when, why. It makes it very difficult to make spurious claims if people want to know how much. I mean, ask yourself, who would you really trust? Somebody who says, well, it's going to be about this much. Or somebody who says 3.5 tons. It's going to be 3.5 tons, plus or minus 3%. Who are you going to trust more? Somebody who has just a kind of a rough estimated vaporous answer, or somebody who can tell you an actual number? And I know if I'm looking for somebody to do a job and I get an estimate from them, they need to stick to that estimate. Well, the same principles should apply in many other fields as well. But one of the things that we really touched on was the fact that it isn't necessarily the numbers many times that matter so much as the rules for handling them. And so really what we're learning is there are rules to everything, and not just numbers. And those rules allow us to manipulate those numbers. Now, when we talk about models, really what makes the model is the rules, not the numbers. Because we might not know what the numbers are, but we know what the rules are for how the thing acts. And the numbers are definitely necessary to give us some idea, some order of magnitude of how effective something will be, or how fast it will be, or how heavy it will be. But if we understand the rules, we can create the model of the thing, and we can try the model out by putting different numbers in it. This is one of the wonderful things about computers. We can put thousands of numbers in there and have it try all these combinations and see which ones look interesting. Now, a perfect example would be, let's say we have a cannonball and it's going to be dropped on a table from a certain height, and we want to know how much damage it's going to do. Well, that's not very hard to figure out. We can see the size of the cannonball, and we know it's made of iron, and without even weighing it, if we can see the diameter of the ball, we can calculate how much iron is there.
and we know the density of iron, or we can look it up and we can figure out how heavy that ball is by using a measurement of its diameter and the measurement or the number for the value for its mass, its density. And a couple of numbers give us the answer, and we know the rules for it. We calculate the volume of a sphere as big as the ball, and we multiply it by the density of iron. We now have a model of that ball, and we can say, well, what happens if we drop it from a certain height? Well, there's a very simple formula, another model, that tells us what's going to happen, how much energy it will gain as it falls in the Earth's gravity, and how fast it will be moving. Well, if we know the mass and how fast it's moving, then there's an equation that tells us its kinetic energy, and that tells us how much damage is going to be done based on what the table is made of. If it's made of plywood, it might not be such a good thing. If it's made of wicker, it certainly won't. If it's made of steel, it might be all right. And so we know, just a native sense of understanding that the different densities and hardnesses of materials might make them resistant. So we've now figured out, by looking at the ball and knowing what it's made of and how far it's dropping, that with about 3 steps, we can actually calculate enough information that we don't have to drop a cannonball on something. We can actually do the math and figure it out. And that really is the beauty of a model. We can describe something, we can slap some equations on it, and we can run it and see exactly what would happen. As you can imagine, there are so many books on mathematics and modeling that it was difficult to pick a good one. But I found one that, to me, I think it really represents the opposite end of the spectrum as well as what we're talking about. It shows the darker side of big math. And it's called The Weapons of Math Destruction by Kathy O'Neill. It was published this year. And the subtitle is How Big Data Increases Inequality and Threatens Democracy. It's a look at how big data is intruding into our lives, and the analysis of this data mining, can produce a picture of somebody that in many ways will violate their privacy, will not leave any stone unturned. And it's a look at how this can actually be misused. And it isn't meant to be a message, stay away from big data or stay away from mathematics, but it's meant to be a cautionary publication that will make you read it and take notice. And on a little bit of a lighter note, I'm also posting a link to a PDF, and it's about learning about math modeling, and it's a very clear and very well-written paper. So I think that if you have any questions about it, this would be a great paper to look at. It's a PDF you can download directly on your computer. It covers learning about mathematical modeling in a very entertaining manner. Now, a lot of people would have a tough time figuring out what computer modeling is doing for them. And I can give you a few really good answers. Weather prediction, knowing where the path of the hurricane is going to go and how much damage it's going to do. That's all computer modeling right there. Making a model of that storm that is tractable. And it takes billions and billions of calculations to make that happen, but it's something we do on a regular daily basis. How about the fact that the weather system influences the growing of our crops and the shipment of our things overseas? We have to know that the ships loaded with goods aren't going to be going into stormy weather and possibly be lost. Many of the things that we're doing these days also have other components of computer modeling built in. For instance, thermostats have digital models built into them that allow them to make predictions about when the heat or the air should come on, so that they try to save you a little energy. And of course, the digital modeling craze is also being taken a little further in some respects, because we now have devices that predict when we're going to run out of milk built into the software in your refrigerator. And we see a lot of devices now with AI, built into them. And these essentially depend on digital models of human behavior in order to operate properly. But it's very easy to fall into a simple trap here, and it's this. Even if we create a good model, a faithful model to the problem, it does not mean that we understand the problem fully, or even if we do understand the problem, it also doesn't mean that we can calculate the answer. You see, some things are so difficult to calculate, or the number of solutions just explodes so fast that there is no way for us to calculate it. And there's a number of very good examples of that available. So how do we know if a problem can be solved at all, if a model will be effective? In large part, it depends on some very simple things. First of all, how many possible answers are there? In many problems that we see, there's a linear relationship between the problem and the number of answers, and it takes a short period of time to figure it out, or it takes a period of time that we can calculate easily enough. We can say, well, it's going to have 6 answers, or 12 answers, or 1,000 answers. And so in those cases, we generally have a means of sorting through the answers rapidly, or discarding a bunch of them, and getting down to the one that makes the most sense. In some cases, the number of answers, however, grows geometrically, and one of these is known as the traveling salesman problem. In the traveling salesman problem, you have a fellow who wants to pass through a number of cities, let's say 6 of them, and each is, of course, at a different distance and a different location, and he wants to do it in minimal time. But he also doesn't want to go through a city twice, because now he's spent money to go somewhere he's already been. So in the traveling salesman problem, the issue is to be able to pass through every city only once, and do it in the shortest time, and that means in the shortest route. Now, the number of solutions for this doesn't seem like a big deal, but it grows faster than you can write an equation for. It's non-polynomial. You don't have a simple relationship between the size of the problem and the number of possible answers, and that's where we run into real trouble. Generating the simplest route can be done by a number of methods, but only the brute force method seems to make the most sense for it. In other words, you simply try all the different ways that you can do it. But here's the rub. You may be able to solve it for 6 or 8 or 9 cities, but pretty soon the number of solutions grows in a way that you can't describe by a simple algebraic or polynomial expression. A lot of problems in our everyday life are simple linear problems. Unfortunately, the problems that make the most sense to study, the ones that are going to give us the deepest answers and the most insight, grow so rapidly, they're non-polynomial, and answering them, calculating them for anything but the very simplest of cases, would take longer than the age of the universe, even with all the computing power on Earth. Now, this is one of the reasons we're looking at quantum computing so intently. Quantum computing allows us to take classes of problems and solve them in a single or 2 or 3 steps, rather than having to go through billions or trillions of calculations to get there. But the unfortunate thing here is we've discovered that even with quantum computing, there are some problems that are truly intractable. A light switch can be in 2 states, on or off. And if we have a box that has 3 switches in it, and those switches can be on or off, we know that there are 8 possible states that box can be in. Many of the systems that we use to control things around us are something like that. They operate a traffic light system, or they run a factory, or they turn our power grid on or off, and we think we understand how that system works. But what happens when somebody throws a light dimmer into the mix with the switches? Now we end up with a number of states that isn't quite predictable. We have a new element that isn't easy to quantify. And what happens if some of these boxes control whether other boxes are being used or not? Sort of like eliminating some of the cities on the traveling salesman route. Our world is based on millions of very simple systems, and some not-so-simple systems, all connected together in ways that produce emergent behaviors, those that we could never imagine in the first place. Some things have happened that we never predicted and we never intended. In a case like this, we can't even generate a model. So where does it leave us? Math and logic give us some pretty simple answers to many things, and we think we understand the systems around us. But we see that even creating a workable model doesn't mean we can work through the model and find the answers properly. We're in a very complicated world. Math and logic have given us a lot of answers, but we know that mathematics is even incomplete. There is no way of encompassing it in a single set of rules. The rules work in such a way as to produce answers that we can't even find. To state it clearly, there are some things we can see are true or false, and there are some things that we can see can be resolved as true or false. We simply don't know how to get there. Modeling can go a long way to help us find answers for many things, but it certainly isn't a guaranteed solution. There are some things that simply aren't even on the map. But you can bet that somewhere there's somebody who's working on a model to show us the answer to that. So at each stage of our intellect, through the development of mankind, we find that there are problems and there are answers. And as the problems became more complicated, or our understanding of them became clearer, we found that some answers could be more difficult to locate, and then we went to computing, where we could increase the speed and the scope of what we could do, in the hopes of finding more answers. Now we're headed for quantum computing, and we find even with that, there are things we can't answer.
So even our best models will fail at some point. And we find that the more we learn and the more we know, the farther the fences around our knowledge recede. We don't even know where the fences are. And that's one of the most important lessons that we've learned. We don't know what the boundaries are. I hope you've enjoyed the show. It was a great interview and some interesting things to think about. And sometimes we have to accept that answers aren't to be found anywhere. But don't lose hope. We have everything we need to make everything we will ever need. This has been Talk Universe. I'm Sir Charles Schultz. We'll talk again.